Good morning, friends. Welcome to the lecture of functional analysis. Today we will try to understand some basic definitions related to functional analysis. There are two topics in all in the functional analysis. First is Banach space, second is the Hilbert spaces. To understand the Banach spaces, we need to understand what is the norm linear spaces. To understand norm linear spaces, let us view the basic definition. Let me share my screen with you. Yeah, this is my screen. Now in this lecture, we will try to understand what is the norm linear space basically and what is the relation between the norm linear space and metric space. To understand what is the norm linear space, or before that what is the linear space, basic definitions are: first is internal composition. Let L be a non-empty set. A mapping from L cross L to L is called an internal composition in L if x star y belongs to L for all xy in L, and that value x star y is unique. Then star is said to be an internal composition in the set L. The very simple meaning is, if we have a composition between the two elements of the same set and the resultant element is also the member of same set, then it is said to be an internal composition. Let us try to understand external composition. Here we have two different sets. Let L and F be two non-empty sets. A mapping from F cross L to L is called external composition in L over F if alpha star x belongs to L for all alpha in F, x in L, and alpha star x is unique. Then star is said to be an external composition in the set L. Again, the very simple meaning of this external composition is, for two different sets L and F, if we take one element from F, one element from L, and we do the composition between the two elements, then this composition is called as an external composition if the resultant element is a member of the set L. Try to understand the definition of a linear space or a vector space. Here we consider F with the two compositions, addition and scalar multiplication, be a field. The element of F are called as a scalar. L be a non-empty set whose elements will be called vectors. Then L is said to be a linear space over the field F if it satisfies the following conditions. The first condition is, there is defined an internal composition in L called addition of vectors denoted by plus symbol, and for this composition L is an abelian group. We know for an abelian group it has to satisfy 5 conditions with respect to addition. First is closure property, second is associativity, third is existence of identity, fourth is existence of invert, and the last condition is commutativity with respect to addition. If any set L together with this addition operation satisfies 5 conditions, then it is called as an abelian group. The second condition for the vector space or a linear space is, there is an external composition in L over F called scalar multiplication and is denoted multiplicatively. That is, alpha x belongs to L for all alpha elements in F for all x elements in L. With this condition, we simply mean that L is closed with respect to scalar multiplication. Now, the next condition for the vector space is, the two compositions, addition and scalar multiplication, should satisfy the following postulates. First is, alpha times x plus y is alpha x, alpha y, where alpha is an element of the field F and x and y are the elements of the set L. Second condition, alpha plus beta times x is alpha x plus beta x. Again here alpha and beta are the elements of the field F and x is an element of L. Third is, alpha beta into x is alpha times beta x. Last condition is 1 dot x is equal to x for all x in L and 1 is the unity element of F. Though these first two conditions looks like distributive conditions, distributive properties, but these are not distributive properties, since for distributive properties we require all the elements to be the member of a same set. But here the elements we are using for the condition are not the elements of the same set. Therefore, these are not distributive. Therefore, whatever conditions we have seen, actually in all there are 10 conditions for the vector space. If any non-empty set together with these 10 conditions is called as a vector space. The simple examples to tell you is, We know a simple example of a vector space or a linear space is a set of all real numbers over set of real numbers is a vector space. R cross R, that is R2, is also a vector space over the field of real numbers. Similarly, we can go to n-dimensional spaces. Rn is also a vector space over R. Similarly, set of all complex numbers is a vector space over the field of real numbers. But the converse is not true. That is, set of all real numbers over the field of complex number is not a vector space because it couldn't satisfy the closure property. We'll try to understand what is a real and complex linear spaces. L is a linear space over the field F. If F is the field of real numbers, then L is called real linear space. And if the associated field is the field of complex field, then the vector space is called as a complex linear space. Simple meaning is, again, if the underlying field is field of real numbers, this is a real linear space. If the underlying field is complex numbers, then this is complex linear space. Next definition is linear subspace. Let L be a linear space over the field F, capital M be a non-empty subset of L, then M is called linear subspace of L if M itself is a linear space over F with respect to the linear operations of vector addition and scalar multiplication. That is, that M should be a subset of a linear space and itself a vector space or a linear space. Coming to the next definition of a metric function. Metric function is actually a distance function. We know what is the distance between the two elements or 2 points in any vector space. Actually, to find out the distance between the 2 points, we use a straight line, that is shortest distance between the 2 points. But in many practical approaches, it is not always possible to take a shortest distance between the 2 points. Then there is a need to define a function which will give us a distance function, and that distance is defined by the metric. Okay, therefore let X be a non-empty set. A metric on X is a real valued function on X cross X satisfies the following condition. First condition is d of xy is greater or equal by 0. Second condition is d of xy is equal to 0 if and only if x is equal to y. D of xy is equal to d of yx. Fourth is d of xy is less than or equals to d of xz plus d of zy for any xyz in x. Actually, this first condition is giving us a non-negativity value because the distance between any 2 points could not be negative. It is either 0 or positive. Second condition tells us that if the distance between the 2 points is 0 is possible only if the 2 points are going to coincide one another. Third condition is if we measure the distance from x to y, it is very similar or very equal to a distance from y to x. And the third condition is called as a triangular inequality. Distance between x and y is less than or equals to, if I take z to be a third point except x and y, then this inequality satisfies. Distance between xy is less than or equals to distance between xz plus distance between zy. Therefore, if any function d satisfies these 4 conditions, is called as a metric function, that is a distance function. Now, the next definition is a metric space. A non-empty set X together with a metric D is called as a metric space and is denoted by XD. Any metric is equipped with a set X, then it is a metric space. Let us generalize the idea of a metric to a norm function, because in the metric function we don't have any idea about what is the distance between the scalar multiplication of the vectors. So for the fourth condition here was given by a norm function. Therefore, norm is again a distance, but instead of considering the distance between the 2 points, it will give us the distance of a point from the origin. Therefore, norm, this is a symbol norm from a non-empty set N to R or C, which satisfies the following axioms. First is norm x is greater or equal by 0. Distance is not negative. This is either 0 or positive. Second condition is norm x is equal to 0. Implies and implied by x is equal to 0. Third, norm of x plus y is less than or equal to norm x plus norm y. Fourth, norm of alpha x is mod alpha times norm of x. If any function norm satisfies these 4 conditions, he is called as a norm function. Next definition is a complete metric space. Any metric space XD is said to be complete if every Cauchy sequence converges to a point of X itself. Let us come to our next important definition of a normed linear space. Let n be a either complex or real linear space. The function norm is a norm on n, means satisfy those previous 4 axioms. Then the ordered pair n norm is called as a norm linear space. Very similar to a metric space, this is set n together with a norm function is called as a normed linear space. Now we'll try to understand what is the relation between norm linear space and a metric space. For this, let us have a look on this theorem. V be a norm linear space, and if a function d of xy is defined as norm of x minus y for all xy in V, then prove that ordered pair Vd is a metric space. That is, V is equipped with norm, and we want to prove that whatever is this d function defined is a metric. That is, norm linear space is given to us, and we want to verify whether Vd is a metric space or not. To verify whether Vd is a metric space or not, we will use all the conditions of norm function, and we will prove all the conditions of a metric function. The first condition to prove is d of xy is greater or equal by 0. Now, according to the given statement, given definition, d of xy is equal to norm of x minus y. Therefore, first, d of xy is equal to norm of x minus y is greater or equal by 0 is obviously true by the first condition of a norm function. Second, we want to prove is d of xy is equal to 0 implies and implied by x is equal to y. Let us start. D of xy is equals to 0. According to the given definition, d of xy is nothing but norm of x minus y. Therefore, d of xy is equal to 0 implies and implied by norm of x minus y is equal to 0. Norm of x minus y is equal to 0 implies and implied by norm of x minus y is equals to 0 according to the second definition of a metric function. And now x minus y is equals to 0 will imply x is equal to y. Hence, we have proved distance between x and y is equals to 0 will give us x is equal to y. Coming to the third condition to prove, that is d of xy is equal to d of yx. Let us start again. D of xy is equal to norm of x minus y. Let me take minus 1 common. Therefore, it is mod of minus 1 times y minus x. Let me use the fourth condition of a norm property, taking the scalar out of the norm with a modulus. Therefore, this is mod of minus 1 taken out into norm of y minus x. But we know mod of minus 1 is plus 1. Therefore, this is nothing but norm of y minus x, which is nothing but d of yx. Hence, the third condition is also proved. Coming to the fourth condition, d of xy is less than or equals to d of xz plus d of zy. Now, to prove this triangular inequality, let us start with d of xy, which we know as norm of x minus y. Let me adjust this z in order to prove the required triangular inequality. Therefore, here in this norm function, we have subtracted and added the z point. Therefore, this is x minus z plus z minus y. Again, we will separate this over the two values x minus z and z minus y by using the triangular inequality of a norm function. Therefore, this is norm of x minus z plus norm of z minus y. Norm of x minus z is d of xz. Norm of z minus y is d of zy. Hence, the fourth property of triangular inequality is satisfied by the given function of d. D of xy is equal to norm of x minus y. Hence, the d is a metric defined on V, and Vd is a metric. That is, if we define or if we start with a norm linear space, it will be a metric space, but converse need not be true always. Let us come to two simple examples. First example is, show that distance between x plus z and y plus z is exactly equals to distance between x and y for all x, y, z in a vector space V. Let us start again. Distance between x plus z and y plus z is given by norm of x plus z minus norm minus y plus z. Now, if we observe the right side here, z will get cancelled automatically, and we remain with norm of x minus y. But we know norm of x minus y is nothing but distance between x and y. Hence, we have proved distance between x plus z and y plus z is exactly equals to distance between x and y. Coming to the next example, distance between alpha x and alpha y is equal to mod alpha times distance between x and y. Distance between alpha x and alpha y is given by the definition norm of alpha x minus alpha y. And we know this is this alpha can be taken common. Therefore, this on the next step we have written alpha times x minus y, but alpha is a scalar again taken out of the norm by a modulus function. Therefore, this is mod of alpha into norm of x minus y, but norm of x minus y is again a metric or a distance x and y. Hence, we have proved this example also. Here we end up with the today's lecture. In this today's lecture, we have tried to understand actually what is the norm linear space, what is the difference between, what is the connection between vector space and a norm linear space, and we have seen that every norm linear space is a metric space, but convert need not be true always. Thank you for watching. We will soon meet with a new lecture. Thank you all.